terms of calculation. So in decimal form. In other words, if it's 5% per year, then we will have to use 0.05. Am I correct? So we're going to look at the time interval t from t to t plus delta t. So we're looking at the time interval delta t of length delta t, and we will take a look at the difference. Balance at t plus delta t minus balance at time t. So what does this difference represent?
The distance?
The distance, or we can say the interest earned during this time interval, right? So this is the interest earned, very good, interest earned during this time delta t, during the time interval delta t. So we will try to approximate, so we will say interest earned at time during the time delta t is approximately equal R times balance times delta t. So this is how we will approximate the interest earned during this time. You can see it's proportional to the balance that we had, and then times the length of the time interval. So R here is, again, it's the interest rate in decimal form. So interest rate times balance, and then you multiply by the length of the interval. So if we use this equation, let's see, we're going to divide by delta t both sides and take limit, let delta t go to 0. So we have divide by delta t, and then we have limit, let limit, take limit. As delta t goes to 0, so we get derivative on the left-hand side, because this is definition of the derivative. On the left-hand side, on the right-hand side, we just get R times P. So we have dP dt derivative equals RP. So this equation should look familiar. This is Malthusian model for population growth. Do you agree?
Yes.
Yeah, we solved this equation last time, except today, instead of considering population, we're considering money, right? This P is the balance at time t, so it doesn't matter whether it's population or balance at time t, the model is the same. So if you integrate both sides, you will be getting P of t equals, well, there is P sub 0, right? P sub 0 times e to the power RT. In other words, we're getting exponential growth here. So let me add here where P sub 0 is, well, it's not population, it's balance at time 0. So here is our model. This is the case when we have interest compounded continuously. So interest here is compounded continuously. Whenever you hear this statement, interest is compounded continuously, you know that this is the model, this is the formula to use for population P of t. So any questions so far? Perfect. Let us try this to use this formula for problem number 2. Let me zoom in a little more. So maybe like this. So I'm going to consider example from the text. It's example 3.4. So let's say you put $1,000 in a savings account with a continuously compounded interest rate of 5% per year. So what is $1,000? What does it represent in this problem?
Not.
P sub 0, right? The initial amount. Do you agree?
Yeah.
So this is P sub 0. It's $1,000. This is the amount we started with. It also says continuously compounded interest rate, 5%. So 5% compounded continuously, those two words, compounded continuously, means this is the formula to use. P of t, because there are other possibilities. If interest is compounded not continuously, but say twice per year or 4 times per year, quarterly, or even monthly, the formula is not going to be this one. The formula will be different. So let's see, P of t equals P sub 0 ERT. So this is the one to use because, again, interest is compounded continuously. So what will be the balance after 40 years? We want to know balance after 40 years. Well, this problem is very straightforward. Do you agree?
Yes.
Very straightforward. So all we have to do is plug in all the constants into the formula and we're done. So P of 40 will be 1,000 multiplied by e to the power. Keep in mind to use the decimal form of the interest rate times 40 years. And using calculators, we should be getting approximately 73.89. And what is the measurement? Dollars, excellent. For some reason, I don't see measurement in the text. I'm looking at this problem right now. They did not provide the measurement. However, let's keep in mind, these are not oranges or apples. These are dollars. And I think it's important to write measurement. And by the way, on your quizzes, I'm thinking I will not ask you to provide any measurement because of so many troubles with computer, with the software when grades are calculated. So, so again, I'm thinking that when it's time for your quiz, I will not ask to provide any measurement. So again, just the numbers, just the number. I'm assuming that you understand that what you're getting is your balance in dollars, right? Balance in dollars. All right, any questions here, this example, 3.4? Perfect, so again, this was the most simple example, the most simple model. Now, next we're going to make it more interesting. So let's suppose that in addition to the interest rate that you earn per year, you also make withdrawals. So let's case 1, let's call it case 1, steady withdrawals. So we have steady withdrawals. This is the case when we withdraw money regularly. So in that case, we have to adjust our model. So it's going to be interest earned during the time interval, delta t, approximately equals. So we still have r times p times delta t. So we still have interest earned in this account, but in addition to that, we have constant withdrawal rate times the time interval. So again, W here is the amount withdrawn per unit time. So where W is the amount withdrawn, the amount withdrawn per unit time, per unit time. So the amount withdrawn per unit time times the length of the interval. Let's divide by delta t and take limit of both sides. Let delta t go to 0. So we get limit, delta t goes to 0. And we have derivative on the left-hand side. On the right-hand side, we have Rp minus W because delta t cancels out. Any questions? So again, this is the limit definition of the derivative. We can replace this by dp dt. On the right-hand side, we have constant r times p minus w. W is also constant. And of course, we also have p of 0 equals some p sub 0. So this is our new model that shows that we have withdrawals, steady withdrawals. What kind of equation do we have here? What kind of equation is this one?
Linear?
Linear, excellent. This is linear differential equation. We know how to solve this. So I'm going to continue here. Let's solve it. What is the integrating factor, A of t?
Is it R?
Excellent, that's correct. R, the number in front of P on the right-hand side, it's R, and that means U of t, the integrating factor. The formula is negative integral R, A of t, right, dt. So we get e to the negative RT. Do you agree with this so far?
Yes.
Thank you. So I'm going to multiply both sides of this differential equation here by the integrating factor. However, first we should move Rp to the left-hand side. So let me start by writing P prime minus Rp equals negative W. So multiply both sides by this integrating factor. Okay, so we are supposed to have derivative of a product on the left-hand side. Let's make sure. Do we have derivative of the product of P times in the integrating factor? Let's see, P prime times E, and then we have plus P times derivative of this exponential function, which is negative R e to the negative RT. Yeah, I believe this looks good. Am I correct?
Yes.
Okay, thank you. So let's integrate both sides. I believe we're ready to integrate. So integral derivative cancel each other, and we end up with p times e to the negative RT on the left-hand side. On the right-hand side, let's keep in mind there is constant in front of t, this minus r, so that will go into the denominator. So this is what I'm getting so far. Any questions, any comments, please let me know. So all we have to do now is simplify and then find c. I'm going to cancel these two negatives. So let's see, we have basically I cancel minus here and minus in the denominator. Divide both sides by e to the negative RT, or alternatively multiply both sides by e to the positive RT. So we're getting our function p of t equals w over r plus c e to the RT. So this is the solution that I'm getting. This is the general solution, because it contains the constant of integration. All I have to do now is plug in 0 for t, so we get p of 0. Let's plug in 0 for t, so we get w over r plus c. E to the 0 is just 1, so we're supposed to have p sub 0. So c is p sub 0 minus w over r. And therefore, our particular solution, this is the final answer, will be w over r plus, and then we have p sub 0 minus w over r times e to the RT. So this is what I'm getting here. Let me check that with the text. So, oh, I don't see, well, it looks like they actually didn't solve it. That's fine. So this is what we're getting here for our particular solution. Are there any questions regarding this case? Case number 1, steady withdrawals. Any questions? Please let me know. All right, let's look at the next model. So case this will be case 2. This is when we have systematic savings. All right, so let's suppose that this time we decide to save 2,000 each year. Assuming that you have no savings to begin with and that your savings will earn 5% per year compounded continuously, how much will you accumulate after 30 years? All right, so I'm going to write down the information first, and then we will try to build the differential equation, the model for this example. So this is example from the text. Again, instead of withdrawals, we have systematic savings. So the savings are 2,000 each year. So savings, which means deposits. You make regular deposits, $2,000 each year. $2,000 per year. All right, so we assume 5% per year compounded continuously. So we have R, 5% compounded continuously. This is important. Compounded continuously. Again, this is very important because it tells us which model to expect. Compounded continuously. How much will you accumulate accumulate after 30 years. So we want to know the balance after 30 years. All right, so we're going to build the differential equation. This is a constant, right? You keep depositing 2,000 per year, every year, no more, no less, it's the same number. So in that case, we will have to account for this situation as follows. So first we still have R times P. Let me correct it. I'm not sure why I put T. It's supposed to be P, R times P. R times P, and then this is because you have interest rate compounded continuously. And then you have to add 2,000. So 2 here represents the number of thousands per year. I'm not going to actually write 2,000. That's a very big number. So any questions? So I don't see the initial condition. So it says, assuming that you have no savings to begin with, and that your savings will earn 5% per year compounded continuously. Well, P of 0 equals to 0, am I correct?
Yes.
So yeah, this is what they say. Initially, you start with nothing in your account. Well, the question arises, how is that possible? How can you start with 0? What will grow at 5% per year compounded continuously? Remember, you keep adding 2,000, right? You keep adding 2,000 every year. So there is something that will, continue growing eventually. So any questions regarding this model? So again, initially it says here, you have no savings to begin with. So when you start, there's nothing there that already accumulated, right? There's nothing. We begin with 0, but then we keep adding 2,000 per year, and we want to know what will be the balance after 30 years. So we want to find again P of 30, right? I have it here, P of 30. Well, let's solve this equation. What kind of equation is this?
Linear.
Linear, excellent. So tell me, what is A of t in this problem?
R.
Excellent. So R, which is given 0.05, I'm going to put U of t over here, negative integral, then we have 0.05 dt, right? So minus 0.05 t. Perfect. So let's solve this dE. I'm going to first subtract 0.05 p from both sides. After that, I'm going to multiply both sides by e to the negative 0.05 t. Okay. Any questions, any comments, please let me know. So again, the left-hand side is supposed to be a derivative of a product, so it's p times e negative 0.05 t prime. So I'm just checking to make sure that this is correct. So p prime times e, And here we're supposed to have plus p times derivative of this exponential, which looks fine. So this is the right-hand side. Integrate, and we have PE negative 0.05t on the left-hand side. Let's be careful integrating this. You can see we have constant in front of t. So this constant goes in the denominator. Plus some c, constant of integration. Any questions or corrections? Please let me know as soon as possible. So again, I'm assuming that you're working at the same time. You have some paper, pencils, right? So you, in order to benefit from this lecture, it's best if you work parallel, right? On your own, just comparing your results with what we have here from time to time. Otherwise, you should be trying to do it independently. It's not good enough to just sit and watch, right? So let's continue. I'm going to simplify. We're almost done here. So let me. I'm just going to quickly check what is 2 divided by negative 0.05 minus 40. And multiply both sides by e to the positive 0.05t. So we get p equals minus 40. And here we have plus c times e 0.05t. So this is the general solution. And to find c, we have to use p of 0, right? P of 0 equals to 0. Let's find c. I believe c is equal to 40, right? And we are getting our particular solution, the answer to this problem. It's negative 40 plus 40 e 0.05t. So this is the particular solution. So any questions regarding this case? Case number 2, when we have systematic savings. This was a simple case when you always add the same number, the same amount per year. So any questions here? By the way, we still haven't answered the question about balance after 30 years. I'm going to complete this. So minus 40 plus 40 times e. And here am I supposed to substitute 30 for t. So all I have to do is type in this formula. And round answer to the nearest cent. So I'm getting $139.27. So any questions? Yeah, it doesn't seem like too much after 30 years.
Don't we have to times that by 1,000 since our initial value was $2,000 per year, but you
yes, you're right. So this is in thousands. You're correct. See, actually you're right. I forgot that we added instead of 2,000, we added just 2, right? So this 2 here was in thousands. You're right, thousands. Otherwise, you're right. That doesn't seem like much. So the actual amount is, this is where I should use, let me see. So 139,267.56 cents. So this is the actual value, right? The balance after 30 years. Otherwise, it doesn't look like much. $139. That doesn't make sense. So any questions here? Any questions? All right, let's talk about planning for retirement. This problem is especially interesting because you could use it for real life to do some retirement planning. So this will be example 3.11. However, I'm thinking I wanted to let you practice a little bit. So let me see. So let us try one of those problems, such as number 3. Let's try number 3 and see how you're doing with this problem. So this is again number 3. From the text, let me display it on the screen. Let me see if I can find it. This is section 3.3. I'm going all the way to the homework problems. This is number 3 right here. So let me zoom in. Or you can simply open your textbook. So let's again zoom further. All right, so let's read the problem. Number 3. Alicia opens an account that pays an annual rate of 6% compounded continuously with an initial investment of $5,000. After that, she deposits an additional $1,200 per year. Assuming that no withdrawals are made and she continues with the same yearly deposit over a period of 10 years, how much will be in the account at the end of the 10-year period? So this problem is very similar to the one we just did, example 3.9. Do you agree?
Yes.
So I'm going to let you try this all by yourself and we'll check perhaps in 5 minutes, right? Should be enough. So please write down the information. If you don't have your books in front of you, write down the information. So there are words here, compounded continuously, right? So you know that what that means, right? We have exponentially growing balance, 6% compounded continuously. So I'm writing down R is 0.06. The initial investment is given, so that would be P sub 0, $5,000. So she started with 5,000. After that, she deposits an additional 1,200 per year. So additional amount she deposits is 1,200 per year. Assuming that no withdrawals are made, She continues her deposits over a period of 10 years. How much will be in the account at the end of the 10-year period? So what is P of 10, right? So that's what we need to find. All right, perfect. So I'm going to give you a few minutes. I'll start breakout rooms. I suggest that you use the lecture notes that I provided earlier, because your model will be very similar, just slightly different numbers. Do you agree?
Yeah.
So I'll give you a few minutes, maybe 3, maybe 5 minutes. The most important part is to create the model, the differential equation, and then solve it to find P of 10. So again, it shouldn't take long. So please join a room. Again, I would like to strongly encourage you to communicate with your classmates. Please, again, don't be shy. This is very important for your learning, that you communicate and try to work together. So I'm going to create about 4 rooms. Actually, let's make it 3. All right, so I'll, again, we'll return and check your computations. All right, please join.